Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to cover the range of a linear map. So in this topic we will define the range of a linear map, consider some consequences of that definition, look at finite dimensional maps and their ranges, and consider the advance and delay operators for the vector space of all discrete time signals. Now, given a linear map mapping a vector space U onto a vector space V, the range is the collection of all vectors in the codomain such that at least one vector in the domain U is mapped onto that vector. Basically, the range of a linear operator A equals all vectors of the form A times U, or A applied to U, where U is each allowed to be every vector in the domain U. You will note that the range of A is a subset of the codomain. Also, we're guaranteed that the range always has at least one element, the zero vector of the codomain. Why is that? Because the domain has a zero vector, and we saw previously that for a linear map, the image of the zero vector is the zero vector in the codomain. Now, here is a theorem that should sound somewhat familiar. If A, mapping a vector space from U to V, is a linear map, then the range of A is a subspace of the codomain V. Proof. Well, what we have to show is that if V1 and V2 are vectors in the range of A, then we must show that a linear combination of these two vectors is also in the range of A. Now, recall that the range of A is a subset of the codomain. So if V1 and V2 are in the range of A, then there must be vectors U1 and U2 in the domain U such that A times U1 is equal to V1 and A times U2 is equal to V2. Notice I'm starting to say times instead of applied to, but both are reasonable. Now, because U is a vector space, we know that a linear combination of the vectors U1 and U2 must also be in that vector space. But wait a second, A is linear. So if we now apply A to that linear combination, because A is linear, the A applied to that linear combination is equal to that same linear combination of A applied to each of the vectors. But wait a second, A applied to U1 is V1 and A applied to U2 is V2. So therefore, the linear combination of the vectors V1 and V2 is also in the range because it is the image of the linear combination of U1 and U2. So, since a linear combination of U1 and U2 is in the domain, it follows that the image of that linear combination is also in the range. Therefore, the linear combination of V1 and V2 is also in the range. Thus, the range is closed under scalar addition, vector addition, and scalar multiplication, and so therefore it is a subspace. Here's a similar theorem. If S is a subspace of the domain U, and A is a linear map taking U onto V, then the image of the subspace S, and you'll recall that we represented the image of a set as A times that set, the image of that set is also a subspace of the codomain V. Well, the proof that's up to you. But it's very, very similar to the previous proof. Theorem. If A mapping a vector space U onto a vector space V is a linear map, then the range of A is equal to just the zero vector if and only if A is the zero map. Proof. If the range of A is just a single vector, then A applied to every single vector in the domain must be equal to that vector, the zero vector, for all vectors in U. However, the zero map is that map such that the zero map applied to U is equal to the zero vector for all vectors U. You will recall that two maps are equal if and only if one map applied to a vector U equals the other map applied to that vector U for all vectors U in the domain. And if that's true, consequently, it follows that the range is just the zero vector if and only if the map is the zero vector. Consequently, if there is at least, so if a map is not the zero map, we are guaranteed there is at least one more vector in the range, and consequently there are infinitely more vectors in the range, as the range is always a subspace. And if there is a second vector in that subspace, then all scalar multiples of that vector are also in the range. Now, if VA is a map that takes vectors in a vector space U and maps them to a vector space V, and the range of A is all of the vector space V, then we say that A is onto. It's also said that A is surjective. Recall that a surcharge is a charge on top of what you're already paying for a product. A surplus is over and above what you need. Thus, a map is surjective if every point in the domain is in some way mapped onto. Now, let's get a more intuitive idea as to what onto is by bringing it back to what you already know. Any odd polynomial that has real coefficients and where the variable is real, such a polynomial maps onto the reals. That is because every single real number is in the range of such a polynomial. On the other hand, no even polynomial with real coefficients of a real variable maps onto the reals. Even polynomials have always a range that is a strict subset of the real numbers. This is because such a polynomial is guaranteed to have either a global minimum or a global maximum, and so nothing is mapped beyond such an extreme point. Now, if t is greater than 0, then the function ln of t maps onto the real numbers. So just imagine ln of t for t greater than 0. You will notice that it doesn't matter what value of you take, you can always find a t such that ln of t equals that value. In fact, it's not hard to find. If you wanted to find that value of t such that ln of t is equal to 1 million, all you have to do is let t equal e to the 1 million. On the other hand, the range of e to the t for real t is the open interval from 0 to 1 to infinity. Therefore, e to the t is not onto the real numbers. On the other hand, if I take e to the t and multiply it by sine of t, then while neither of these functions is onto the reals, if you were to plot their product, you'd notice that yes, the range of e to the t times sine of t is in fact every real number. Now, here's an interesting challenge for the top students in the class. Prove that every non-constant polynomial with complex coefficients where the variable is assumed to be any complex number, prove that that polynomial must map onto the complex numbers. And I'll give you a hint. You already have all the tools necessary to prove this. Now, let's return back to finite dimensional linear mappings. And you'll recall from the last lecture, every finite dimensional linear mapping can be represented by a matrix. So if A is a linear mapping from f to the n to f to the m, so A is an m by n matrix, then the range of A equals the span of the column vectors. In other words, if A is this matrix of n columns, then the range of A is simply the span of those n vectors. You can, of course, use Gaussian elimination to find a basis for the range. For example, here's the matrix A. It is 4 by 5, and therefore it maps r to the 5 to r to the 4. So therefore, the codomain is a 4-dimensional vector space. Now, if we wanted to determine a basis for the range, of course, the range is just all linear combinations of those 5 vectors, but if we want some more information, we can find a row equivalent matrix. Now, here I am not using partial pivoting because all we're interested in are those columns that contain leading non-zero entries. And we see that columns 1, 2, and 5 contain leading non-zero entries. Therefore, a basis for the range are columns 1, 2, and 5 of the original matrix A. So the vectors 1, 3, 4, negative 2, 2, 8, 14, negative 8, and negative 2, negative 2, 7, negative 10. Those 3 vectors are linearly independent, and therefore their span is a 3-dimensional subspace of r to the 4. If you wanted, you could also apply Gram-Schmidt to these 3 vectors to create an orthogonal or orthonormal basis for that range. Also, for finite dimensional vector spaces, the dimension of the range of A is just equal and always equal to the rank of A. And A is onto if and only if the rank of A is equal to M. Now, I'd like you to recall the delay and advance operators for discrete time signals. So if x is this discrete time signal, because the delay operator applied to x is simply all of the entries in x shifted over by 1, and the first entry is 0, it becomes clear that the range of all of the delay operator is all signals where the first entry is 0. On the other hand, the advance operator moves all of the entries to the left and discards the first entry. Well, in that case, you could give me any discrete time signal, and it's not hard to simply shift all of them over by one, and that becomes a vector that the advance operator maps onto the vector you gave me. So therefore, the range of the advance operator is still all signals. So, following this topic, you now know the definition of the range of a map. You know that the range of a linear map is always a subspace of the codomain. You have become familiar with some additional results relating to the range, and you understand the definition of a map being onto. You know how to determine the range of a finite dimensional linear map, and you know how to determine if such a map is onto the codomain. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!